Today I want to present to you a quite unconventional and convoluted proof for the little Gauss sum formula. Let's start with a fact about lines, specifically lines connecting two grid points on the square grid. This fact holds for any line connecting 2 points on the square grid, and it's about the x and y difference between the start and end point of the line. Let's call them delta x and delta y. For example, this line is 6 units high, so its delta y value is 6. Now we increase the delta x value to 4. Now let's look at the slope of this line. It's delta y divided by delta x, meaning it's 6 divided by 4, or 3/2. Now let's look at how many points lie on this line. If we step one x value to the right, y increases by exactly the slope, 6/4. 6/4 is the same thing as 3/2. That means we can cancel out a factor of the GCD of delta x and delta y. GCD here meaning the greatest common divisor of those numbers. Now the slope is 3/2. If x is increased by 1, then delta y increases by 3/2. Now every time we hit a point, both of the coordinates have to be integers. So 3/2 multiplied by the x value has to be an integer. That means x has to be divisible by 2. Now in general, delta x has to be divisible by delta x divided by the GCD of delta x and delta y, because delta x is just the bottom part of the fraction times the GCD of delta x and delta y. Now this means that if we go from the x value of 0 to delta x, which is 4, then we get delta x divided by this value plus 1 number of points, because we have to count the first one, that's why there's a plus 1, and we have delta x steps to go through. So our total number of points is just the GCD of delta x and delta y plus 1. Now let's get to a different part of math, and let's explore the so-called Pick's theorem. Pick's theorem concerns itself with the area of so-called Pick polygons. Those are simple polygons, meaning they don't have holes or self-intersections, and also their corner points lie on the square grid. Pick's theorem now states that the number of inner points of this polygon plus half of the number of boundary points minus 1 equals the area of this polygon. Now I also have a short non-rigorous sketch of a proof for you today. Let's start with showing that all elementary triangles
Elementary,
meaning triangles with only 3 boundary points and 0 inner points, always have an area of 1/2. If we fill the whole plane with those elementary triangles, we get a filled plane actually, because all triangles tile the plane. Now if we consider a certain region on this plane, for example a square, and then look at the number of points that are in it, in the limit this converges to the same as the area of this region, because every point corresponds to 1 unit area exactly. Now if we look at how many points are on the boundary of a triangle, it's 3, because they are all elementary. If we look at how many triangles touch each point, then that number is 6. This means that the ratio of points to triangles in this area, in this region, is 3/6, or 1/2. But because the number of points is also the area, this is also the ratio between area and triangles, meaning that one triangle has the area of 1/2 because all of the triangles have the same area. Now let's also prove the so-called additivity of pig polygons, specifically for elementary triangles and some other polygon. If we just concatenate the elementary triangle with the polygon and they meet in 2 points, then the polygon gains one boundary point, meaning that its area, according to Pig's theorem, increases by 1/2, which agrees with the fact that elementary triangles have area of 1/2. Meaning that if the first polygon was abiding Pig's theorem, then the new polygon does as well. If the triangle has 3 points in common with the original polygon, then the original polygon gains one inner point, but loses one boundary point, exactly the point that it gains in the inner points. So according to the formula, 1 is added and then 1/2 is subtracted. So in total, also 1/2 is added, which is the area of the triangle. So this means that if we concatenate a elementary triangle with a polygon, then the polygon is also a pig polygon if the first one was. Now let's consider the set of all pig polygons that don't obey Pig's theorem. So if this set is non-empty, then Pig's theorem wouldn't be true. Now let's also take out the polygon in this set with the smallest possible area. Now if we chop off a elementary triangle off of this polygon, which is always possible because this polygon isn't an elementary triangle because all of those obey Pig's theorem, so it's always possible to chop one off. Then we can see if that both of these have a smaller area than the original polygon, so they have to obey Pig's theorem because they won't be an S because we chose the polygon with the lowest area. So these are both pig polygons. Now if we concatenate them again, by additivity we again get a pig polygon. So this is a contradiction because we said this was not a pig polygon, but we just proved it is. This means that S has to be an empty set, so every pig polygon obeys Pig's theorem. Now, there are also some extensions to Pig's theorem. Specifically, all parallelogram grids also obey Pig's theorem. This also includes the equilateral triangle grid because it is equivalent to another parallelogram grid. But Pig's theorem can't be expanded onto any other grid, for example, the hexagon grid. Only parallelogram grids work, but this is a story for another time. Now let's recall all lines that connect 2 points on the square grid have the number of points on them that correspond to the GCD between the x and y difference of the start and end points of these lines plus 1. So in general, the points on a line are the GCD of delta x and delta y plus 1. This can be used to compute the number of boundary points of a polygon. The GCD of the x and y difference between any consecutive corner points of the polygon. The plus 1 just falls off because otherwise every corner would just be counted twice. Now you might see where this is going. If we now consider a right-angled triangle on the square grid and call one of its lengths A and the other one B, then the number of points on its diagonal is exactly GCD of A and B plus 1. Now also the points on the other sides count. Those are just A and B, so the total number of boundary points is GCD of A and B plus A plus B. If we now consider the diagonal of this triangle as a function, we see that this function would be y equals b minus b over a times x, where the coordinate grid lies exactly on the straight edges of the right triangle. Now for each x value, the y value is given by this formula, and the number of points on this x value is just the floor function of the y value. This can now be used to count the number of inner points contained in this triangle, but it overcounts because it also counts the edge points, meaning we have to subtract those. Now the area of this triangle is obviously a times b over 2, and now we can use all those formulas and plug them into Pick's formula to get a formula for the GCD. I've left out all the algebraic details because I think they don't matter as much. But now we can rearrange this equation for the sum and set a equal to b. Now if we replace all the b's with a's, now we see that the sum from k equals 1 to a of k, so just the sum of the first a natural numbers, is equal to a plus 1 times a over 2, which is exactly the little Gauss sum formula. I was a little short on time when making this video. I hope you still enjoyed it and I hope you got something out of it. This isn't meant to be an actual proof for the little Gauss formula. I think this way of proving it also shows a lot of insight into different areas of mathematics. And as always, the path is the true destination. So thank you for watching and leave any comments, corrections or anything else down below. Bye bye.